Bismillahirrahmanirrahim. On behalf of ComSec's Institute of Information Technology's virtual campus, I welcome all of you into today's lecture. Today is our 23rd lecture of the Fluid Mechanics series, and I'm your instructor, Dr. Fahd Munir Abbasi. Starting with the layout, in today's lecture, we'll initially go through the highlights of the previous lecture, what we have done in the previous lecture, what were the concepts which were analyzed. We'll go through in that in detail. Then today is say very important lecture. This is one of the most important lecture, as we are going to discuss the most important equation in the fluid mechanics for you people up till now, and that is the Navier-Stokes equation. Navier-Stokes equation की importance बहुत ज़्यादा, utilization बहुत ज़्यादा, because this is the closest form or more realistic form compared to the other equations which we have studied so far. So आज का lecture बहुत ज़्यादा important इस भी वजह से है कि ये जो Navier-Stokes हम equations हम आज के lecture में discuss करेंगे, इनकी utilization above all the previous equations which we have discussed so far बहुत ज़्यादा, practical applications बहुत ज़्यादा, and I'll tell you when I'll go through these equations that how we utilize these equations in solving different type of flow problems in fluid mechanics. Then we'll perform the detailed analysis of Navier-Stokes equation. Term by term इसका detailed analysis करेंगे. जैसा कि गाहे बगाहे मुख्तलिफ equations जब भी हम solve करते हैं तो मैं कोशिश ज़रूर करता हूँ उसका analysis ज़रूर किया जाए, so that you people become familiar कि what is the physics or what is the meaning behind these mathematical equations. So आज की भी Navier-Stokes equation के अंदर जब हम उसको derive करेंगे तो उसकी मुख्तलिफ terms को take into account करेंगे, and will tell you कि क्या relation है इस equation का with the previous equations जो कि हमने derive की and solve की in several cases. So this lecture is very important, and again I would say कि previous lecture में और उससे पिछले lecture में भी जो मैं आपको मुसलसल कहता रहा कि चीज़ों को summarize कर लें, चीज़ों को compile कर लें, अभी तक के लिए जो कुछ आपका knowledge है fluid mechanics का, जो कुछ इन 20-22 lectures में हमने किया, इनको एक दफ़ा summarize करके go through कर लें ताकि आप upcoming analysis के लिए तैयार हों. तो I was making you prepare for this stage or the Navier-Stokes equations, which are the most important equations in fluid mechanics up till now for the Newtonian fluids, obviously. So it's about time to make you people familiar with the Navier-Stokes equations. Well, in the previous lecture we studied about the applications of the Bernoulli's equation. हम Bernoulli's equation को पिछले दो lectures से discuss तो कर ही रहे हैं. In the 21st lecture we studied about the derivation of the Bernoulli's equation. किस तरीके से Bernoulli's equation को derive किया जाता है by integrating the Euler's equation of motion. हमने Euler's equation of motion को integrate किया था separately into rotational field about a streamline and into an irrotational flow field in a random direction. दोनों केसेस के अंदर हमने देखा Bernoulli's equation की क्या फॉर्म बनेगी और Bernoulli's equation के कांस्टेंट की क्या वैल्यू होगी, Bernoulli's कांस्टेंट की क्या वैल्यू होगी, और then we saw that this equation or the Bernoulli's equation gives us the energy balance equations, and each term in the Bernoulli's equation has the dimensions of length, and that's why we named it as we attached the name head with each term, and we named them as elevation head and the kinematic head and the pressure head respectively, and a total head which was the sum of all these heads. तो ये तो Bernoulli's equation से related चीज़ें चल रही थी, but in the previous lecture हमने इस particular equation की applications को discuss किया. जितनी applications किस किस तरह से इनको utilize किया जा सकता है, किस किस तरह से Bernoulli's equation हमारे लिए helpful है in certain type of flow problems, किस तरीके से हम discuss करते हैं, किस तरीके से हम कोई चीज़ find out कर सकते हैं making use of this equation. ये was the say center of gravity of our previous lecture. हमने मुख्तलिफ जगहों के ऊपर velocity field find out की, making use of the Bernoulli equation. Pressure find out kiya making use of the Bernoulli equation. I discussed with you the example of a water tank and that of a spillway of a dam, and I told you at that point that you can see the applications of the Bernoulli equation in these two examples. Then we discussed some limitations of the Bernoulli equation. Bernoulli equation की कुछ limitations फिर आपसे discuss की थी और at the end of the previous lecture, and I told you कि कुछ चीज़ें ज़रूर हैं जो कि limit करती हैं Bernoulli equation को. हम Bernoulli equation को हर जगह पे implement नहीं कर सकते, और अगर हम करेंगे भी तो वो इतने precise रिजल्ट्स हमें नहीं मिलेंगे, क्योंकि कुछ चीज़ें ऐसी हैं जैसे कि हम बर्नौली इक्वेशन के अंदर हम फ्रिक्शनल लॉसेस को इग्नोर कर देते हैं ड्यू टू विस्कस इफेक्ट्स, बिकॉज वी आर अंडर द सुपोजिशन दैट वी आर डीलिंग विद द आइडियल फ्लूइड्स. तो जितने भी फ्रिक्शनल लॉसेस विस्कोसिटी की वजह से होते हैं हम उनको नेगलेक्ट कर देते हैं, जो कि ज़्यादा अच्छी अप्रॉक्सीमेशन हमें नहीं देता है फॉर द केस ऑफ रियल फ्लूइड्स और ऐसे केसेस में जहाँ विस्कस इफेक्ट्स डोमिनेंट होते हैं. अगेन और कर्व्ड पाथ्स या कर्व्ड चैनल्स या कर्व्ड ज्योमेट्री के अंदर चूंकि हमें सेंट्रीफ्यूगल फोर्स को भी टेक इनटू अकाउंट करना पड़ता है, जो कि बर्नौली इक्वेशन के अंदर नहीं मौजूद पहले से. सो उस इक्वेशन की केस के अंदर भी बर्नौली इक्वेशन इतने अच्छे रिजल्ट्स नहीं देती. तीसरी जो चीज़ थी दैट वाज रिलेटेड टू दैट we have considered no external force except the gravitational force in the derivation of the Bernoulli equation. So any external force which is acting on the fluid will have to be created separately from the gravitational force in order to be in order to get good results which are compatible with the experimental readings. Then at the end of the previous lecture I told you about the practical applications of Bernoulli equation. I shared say a couple of names of the instruments which make use of the Bernoulli equation or the Bernoulli's theorem to measure the discharge rate or to measure the velocity at any point in a stream. And in today's lecture it's time for the Navier-Stokes equation. These equations देखें स्टेप बाय स्टेप चले. मैं एक दफ़ा ये नेवियर-स्टोक्स इक्वेशन कम्प्लीटली डिराइव करने के बाद भी आपको ये पैटर्न नोट कराऊंगा जो कि अभी कराने लगा हूँ. बट कीप दिस थिंग इन माइंड, हम बेसिक हाइड्रोस्टैटिक इक्वेशन से चले विच वाज फॉर पर्टिकुलरली फॉर फ्लूइड इन स्टैटिक इक्विलिब्रियम, जहाँ पे एक बहुत बड़ी रिस्ट्रिक्शन हमने ये लगाई थी. ऑब्वियसली वी एट दैट टाइम वी वर dealing with the fluid statics and now we are moving towards the fluid dynamics. So fluid was in static equilibrium at that time. This was the assumption. अच्छा, ये एक assumption थी और हमने balance of force find किया for a static fluid or for a fluid which is in static equilibrium. Then we move towards the Euler's equation of motion. हमने Euler's equation of motion को discuss किया और उसके उस टाइम के ऊपर restriction एक थी कि fluid is moving but the fluid which is under consideration is ideal fluid or there are no viscous effects or no viscous forces acting on the fluid, which was a big restriction as well because अगर आप इस सारी चीज़ों को जो कि फ्लूइड मैकेनिक्स के कोर्स को हम जैसे जैसे परस्यू कर रहे हैं आप रिकॉल करें तो आई टोल्ड यू एट दैट टाइम इन द बिगिनिंग that most of the fluids or almost all the fluids occurring in this nature or universe are viscous fluids and real fluids, not the ideal fluids. They can be Newtonian, they can be non-Newtonian, but the very rare case that the fluids are ideal fluids. Yet we consider some of the fluids as ideal fluids, as we treat gases as ideal fluids when they have very low viscosity and the viscous effects are negligible. अब चूंकि ज़्यादातर फ्लूइड्स जो हैं वो विस्कस इफेक्ट्स जो हैं वो शो करते हैं, सो आयलर्स इक्वेशन ऑफ मोशन किस तरीके से इतनी ज़्यादा कंपैटिबल होगी ये चीज़ देखने की ज़रूरत थी. सो दिस वाज अ बिग रिस्ट्रिक्शन कि जब हम विस्कस इफेक्ट्स को इग्नोर कर रहे थे. नाउ एज फार एज द नेवियर-स्टोक्स इक्वेशंस आर कंसर्न, जब हमने स्टोक्स इक्वेशन कपल ऑफ लेक्चर्स अगो जब I went through the topic of the Stokes equation, I told you that these are the stresses, the normal and the shear stresses which we have calculated for the Stokes equation. This the name Stokes which you are looking at in the Navier-Stokes equation is the same Stokes who proposed those equations, and these equations are proposed by these two scientists collectively and known as the Navier-Stokes equation. These equations are valid for real Newtonian fluids, and these are the force balance equation for real moving viscous fluids. Now we'll start with the law of conservation of momentum, and the mathematical form is given in equation 1. On the left hand side there is rho is the density of the fluid, and dv by dt is the total derivative of the velocity of the fluid. Now dv by dt is the total derivative of the velocity of the fluid, and rho is the density of the fluid. Again, this b is the body force, and this t with an underbar under it is the Cauchy stress tensor. Keep things in your mind which we have studied previously. We are familiar with the term rho, which is the density. We are familiar with the body force term because we have used it in the basic hydrostatic equation and in the Euler's equation as well, in the form of, say, gravity, and in some cases at that time as well we considered the cases of different body forces as well by introducing an F into it. तो यहाँ पे ये B भी body force को represent कर रहा है. This rho is the density of the fluid, this V is the velocity of the fluid, T here is time, but this capital T is the Cauchy stress tensor. This is a new thing for you, but this is divergence of the Cauchy stress tensor. Now for viscous fluids, this stress tensor is equal to minus P and this I. Again, this P is pressure, this I is the identity tensor, and this mu is the viscosity, and A1 is the kinematic tensor, which is defined in equation 3. Now analyze this equation separately. This Pi is the indeterminate part of the stress tensor, mu is the coefficient of the viscosity, and A1 is the kinematic tensor defined by the sum of gradient of velocity and transpose of the gradient of velocity, and we have named it as equation 3. As a student of mathematics, you should be familiar with the term gradient and how to calculate the gradient, because we have been doing it, and then the transpose itself, that how we calculate the transpose of a matrix, and we calculate that. So this A1 will be in the form of a tensor. ये तो एक प्रेशर ही था, बट जब आइडेंटिटी टेंसर के साथ इसको मल्टीप्लाई या आइडेंटिटी मैट्रिक्स के साथ इसको मल्टीप्लाई किया जाएगा तो इट विल बिहेव एज अ टेंसर इटसेल्फ. सो फॉर विस्कस फ्लूइड्स ये चीज़ ज़रूर ज़हन में रखें. ये जो चीज़ मेंशन्ड है, ये जो phrase mentioned here, this is very important, that for viscous fluids tau is equal to minus Pi. Whenever we are dealing with the non-Newtonian fluids, this relation or relation 2 will not hold in its in the manner it is written here. Non-Newtonian fluids के लिए again ये relation Cauchy stress tensor का, it will be far more different from this one written here. So the relation of the Cauchy stress tensor, which is given through equation 2, is valid for the viscous or the Newtonian fluids only. Now in component form, equation 1 can be written as rho du by dt, which is the x component of the velocity, partial by partial x sigma xx. हमने Cauchy stress tensor, जब stress को हमने tensor की form के अंदर लिखा था, तो ज़रूर एक चीज़ आपके जहन के अंदर, मैंने उस वक्त भी उसको काफ़ी ज़ोर दे के एनालाइज़ किया था और ज़ोर दिया था इस चीज़ के ऊपर कि कीप दिस थिंग इन माइंड कि किस तरीके से हम स्ट्रेस टेंसर को लिख रहे हैं और किस तरीके से हम इसको यूटिलाइज़ करेंगे. हम नॉर्मल स्ट्रेसेस किन को कहते हैं, डायगोनल एलिमेंट्स क्या हैं, और नॉन डायगोनल एलिमेंट्स किन चीज़ों को रिप्रेजेंट कर रहे हैं. सो यू शुड बी फेमिलियर विद दैट. एंड अगर नहीं है तो चलो मैं एक दफ़ा दोबारा उसको रिकॉल कराता हूँ. अगर आप स्ट्रेस टेंसर को या टेंसर नोटेशन को देखें, जब हमने स्ट्रेस को मैट्रिक्स की फॉर्म के अंदर, टेंसर की फॉर्म के अंदर लिखा था, तो हमने डायगोनल एलिमेंट्स को सिग्मा xx का नाम दिया था, सिग्मा yy एंड सिग्मा zz. Tau xy and tau xz. Here it was tau yx, tau yz, tau zx, tau zy, and this was, say, stress tensor. अगेन अगर आप इसको सिर्फ स्टोक्स इक्वेशन के कॉन्टेक्स्ट में भी देखें तो देयर वाज अ ए बी एंड सी रिटन इन द डायगोनल एलिमेंट्स and non-diagonal elements पे f, g and h were written which were symmetric, the whole tensor was symmetric. Now इस स्ट्रेस टेंसर को दोबारा रिकॉल करें तो ये जो डायगोनल एलिमेंट्स थे ये नॉर्मल स्ट्रेसेस को रिप्रेजेंट कर रहे थे. यही वजह है कि हमने टाउ से रिप्रेजेंट करने के बजाय इनको सिग्मा से रिप्रेजेंट किया था. अदरवाइज आप इसकी जगह टाउ एक्स एक्स भी इसी तरह लिख सकते हैं, टाउ वाई वाई एंड टाउ जी जी. बट just to make the difference that these are normal stresses, we make use of the notation sigma here with the subscript II to represent the normal stresses, whereas the non-diagonal elements represent the shear stresses. So shear stresses represent कर रहे हैं ये non-diagonal elements, whereas normal stresses are being represented by these diagonal elements. अब अगर इस stress tensor की divergence और डेल ऑपरेटर का डॉट प्रोडक्ट विद दिस टेंसर कैलकुलेट किया जाए तो आपको कंपोनेंट फॉर्म सेपरेटली कैलकुलेट करने में और उसको डिटरमिन करने में आसानी होगी. जैसा कि दिस होल रो इज व्हेन divergence of this tensor is calculated, this will be in the x component, then the second row will be in the y and third row will be in the z component as it is given in equation 3, 4 and 5 respectively. Let's see how the component form of equation 1 is made up. On the left hand side there is rho du by dt, obviously because it was d v by dt, so the x component will deal with the total derivative of the x component of velocity. So here it is du by dt. On the right hand side it's partial by partial x sigma xx. Again this is the x derivative of the normal stresses in the x direction here. Here this normal stress is derivative with respect to x because it is in the x component of the momentum or of the Navier-Stokes equation, plus partial by partial y because it is divergence, and tau xy which is the shear stress and the second member or second identity in the first row, plus partial by partial z tau xz here and plus the x component of the body force. The y component of the Navier-Stokes equation given in equation 4 reads that on the left hand side it's rho dv by dt. Again, since v is the y component of the velocity, as simply v u v and w and del operator is equal to partial by partial x, partial by partial y and partial by partial z here. So you should be familiar, you are in fact familiar with these two terms. So the y component is rho dv by dt equal to partial by partial x tau yx, which is the first identity in the second row of the stress tensor. Here it is plus now the normal stresses in the y direction is derivated partially with respect to y itself. So it's partial by partial y sigma y plus partial by partial z tau y z plus rho b y, named as equation 4. Now then equation 5 gives the z component of the Navier-Stokes equation, which is rho dw by dt, where w is the z component of the velocity, equal to partial by partial x tau zx, which is the first component of the third row of stress tensor, partial by partial y tau zy, which is the second component in the third row, and partial by partial z sigma z, which is the normal stress in the z direction, plus the z component of the body force. Now note that d by dt is the material or the total derivative. We have written it and we have proved it that the total derivative is the sum of the local rate of change plus the convective rate of change. So दोनों changes, दोनों type के changes को मिला के convective change, total change हमें मिलेगा. So this total change written here is the sum of this local rate of change and the convective rate of change. Now as if you recall the Stokes equation, which we used a couple of lectures ago when we are going through the deformation of the fluid, then tau yx and tau xy are equal to mu times partial v by partial x and partial u by partial y. So since it is tau's xy component or shear stresses xy component, so the y component of the velocity is derivated with respect to the x component, and the x component of the velocity is differentiated with respect to the y component. Similarly, tau yz, because it's symmetric, so it is equal to tau zy equal to mu times partial w by partial y plus partial v by partial z, and tau zx is equal to tau xz equal to mu times partial w by partial x plus partial u by partial z. These were the 6 components of the shear stresses, whereas the normal stresses, the sigma xx, sigma yy, sigma zz are also given as minus p minus 2 by 3 mu del dot v plus 2 mu partial u by partial x. Again I'm saying, and us mauke pe bhi I told you that there is no need to memorize these equations. You can simply understand them and write it anytime you like, whenever there is no need to memorizing it or cramming it. इन equations को रट्टा मारने की बिल्कुल ज़रूरत नहीं है. इनको आप अगर थोड़ा सा closely analyze करें और समझने की कोशिश करें तो you will be able to understand the logic and how to write this equation. The normal stress is sigma xx. Obviously there is a pressure with the minus p, and then there is minus 2 by 3 mu times del dot v plus 2 mu partial u by partial x. This is the normal stresses in the x direction. Now sigma y, it is minus p minus 2 by 3 mu del dot v plus 2 mu partial v by partial y, and sigma z is all the same except for the last term, which is 2 mu partial w by partial z. So these were the Stokes equation which calculated the shear and normal stresses for the fluid. We'll make use of these stresses, these 9 component of the stresses in the component form of the Navier-Stokes equation, and substituting these values into equation 3 to 5, we get that rho du by dt. We have substituted here the value of tau xy, sigma xx here, which is the normal stress in the x direction, and differentiated in partial by partial x. This was equation 3, and we have just substituted the values of shear and normal stresses into this equation. तो इन नॉर्मल स्ट्रेसेस और shear स्ट्रेसेस की वैल्यू सब्स्टिट्यूट करने के बाद जो वैल्यू जो इक्वेशन की फॉर्म बनी, x कंपोनेंट को हमने इक्वेशन 6 कह दिया, y कंपोनेंट को हमने इक्वेशन 7 कह दिया, और z कंपोनेंट को हमने इक्वेशन 8 कह दिया. Consider that इस चीज़ को देखें कि यहाँ सिग्मा एक्स एक्स की जगह हमने नॉर्मल स्ट्रेसेस सब्स्टिट्यूट किए हैं, वेयरएज टाउ एक्स वाई की जगह शीयर स्ट्रेसेस एंड टाउ एक्स जी की जगह शीयर स्ट्रेसेस, और बाकी दोनों कंपोनेंट्स के अंदर भी सेम इज़ द केस. And this equation 8 is the z component of the Navier-Stokes equation after substituting the value of the shear and normal stresses. Now equations 6 and 8 can also be written as equation 6 और equation 7, 8 को हम also लिख सकते हैं by taking this pressure term out of the normal stresses. Normal stresses के अंदर जितने भी pressure term appear हो रहे हैं, take for instance this equation 6 के अंदर due to normal stresses there is a partial derivative of pressure with respect to x because it's the x component of the Navier-Stokes equation. तो हम इन तीनों equations में से pressure को separately outside this term भी लिख सकते हैं. तो we have just simply written it down in this manner. It's just minus partial p by partial x and rest of the equation remains the same. So हम pressure को separately भी लिख सकते हैं in this Navier-Stokes equation, and we have named the three components of this equation as equation 9, equation 10 and equation 11 here. So equation 9, 10 and 11 को are the x, y and z components of the Navier-Stokes equation written with pressure separately. Now these set of equations, and that is equation 9 to 11, is referred to the famous Navier-Stokes equation. ये जो equations 9 to 11 है, these are known as Navier-Stokes equation. This equation 9, 10 and 11, these are the x, y and z components of the Navier-Stokes equation. Now it's very important to analyze these equation term by term and one by one, कि हम इन equations को ज़रा study करें in different manner and analyze them in a different way. Left hand side पे अगर आप थोड़ा सा इसको गौर करें, there is a total derivative appearing here, and I told you that this is the sum of the local and the convective rate of change. Then there is a derivative of pressure, and then there are derivatives of the stresses, the normal and shear stresses plus the body force. और अभी तक के लिए body force पे हमने कोई specification नहीं लगाई that it is the gravitational force or it can be the electromagnetic force. So it is a very generalized sort of equation at this point of time. So these equations, equation 9 to 11, are the x, y and z components of the Navier-Stokes equation. A considerable simplification occurs in the problems where viscosity can be considered constant. जहाँ पे viscosity को अगर हम constant consider करें तो फिर काफ़ी सारी simplification इस equation के अंदर हो सकती है. I have written here these equations in the simplified form. You can also say calculate these equations and solve this. अभी तक के लिए viscosity is written within the derivatives here in equation 9 to equation 11. अगर viscosity is constant here, then we can write this viscosity outside this derivative, and we can simply apply the derivative on the other terms in the bracket. So अगर constant viscosity consider की जाए तो फिर very simplified form of Navier-Stokes equation can be gathered, which is given through equation 12 to equation 14. This gives the Navier-Stokes equation for the constant viscosity fluid. Again, there is a simplification here, or you can see that only one term with minus 1 by 3 mu partial by partial x del dot v occurs here, and rest there is del square of u. अगर आप देखें तो Laplacian operator del square partial square u by partial x square partial square u by partial y square and partial square u by partial z square is here, and the x, y and z components of the body force are there. Similarly, in the y component of this equation, there is partial square v by partial x square plus partial square v by partial y square and partial square v by partial z square, and in the z component is the Laplacian of the z component of the velocity. So अगर viscosity को constant treat किया जाए तो then a considerable simplification of the Navier-Stokes equation can be made. एक और चीज़ जिसकी तरफ अभी ही नेक्स्ट एक दो स्लाइड्स के अंदर तो उसको डिस्कस करेंगे, बिकॉज वी आर गोइंग टू एनालाइज डिफरेंट forms of Navier-Stokes equation and we are going to analyze it term by term. तो एक और चीज़ की तरफ ज़रूर आपकी तवज्जो दिलाना चाहता हूँ, which is the second term on the right hand side. I'm talking about this term. जितना कोर्स हमारा मैच्योर हो चुका, आज 23वां लेक्चर है, तो एट दिस पॉइंट ऑफ टाइम यू पीपल शुड बी एबल टू सी थ्रू दीज इक्वेशंस कि अब इसके अंदर मजीद हम क्या कर सकते हैं. सो एट दिस पॉइंट यू शुड बी एबल टू सी कि मजीद इसके अंदर क्या कंसिडरेशन और क्या सिंप्लीफिकेशन की जा सकती है, मेकिंग यूज ऑफ सर्टेन थिंग्स विच वी हैव ऑलरेडी लर्नड बिफोर. So you can see this del dot v here, the divergence of the velocity here, and this term should remind you about something which we have already done in our course. So let's move on. That if the fluid is incompressible, so if the fluid is incompressible, then what we get and what we know already about the incompressible nature of the fluid. For incompressible fluids, the continuity equation incompressible fluids के लिए continuity equation you should be recalling that it gave us that divergence of the velocity field or del dot v is equal to 0 where rho is constant. जब भी incompressible fluids के लिए the continuity equation gives that del dot v is equal to 0. Incompressibility means that the density remains constant. It is not the function of pressure or the temperature. So for incompressible fluids, the divergence of the velocity field is equal to 0, and this is the thing which I was telling you in this slide, that you should be able to look through that this del dot v is appearing here, so we can simplify it for the incompressible fluids. जब भी हम incompressible fluids को consider करेंगे तो ये del dot v की जो term है ये हमारे लिए जो है मज़ीद simplify हो जाएंगे. This term vanishes out for incompressible fluids. Because this del dot v is equal to 0, so this term will vanish out, so only 3 terms will survive on the right hand side of this equation. So simplified form of the Navier-Stokes equation for an incompressible fluid whose viscosity is constant are given through equations 15 to 17. Equation 15 is the x component of the Navier-Stokes equation. Equation 16 is the y component of the momentum equation, and equation Navier-Stokes equation. These are also sometimes referred to as the momentum equation. That's why I keep on saying it again and again and again. I'll talk about that once I finish these equations. And equation 16 is the z component of the Navier-Stokes equations. Simply now if you look at the terms, the left hand side remains the same. It is the total derivative of the x component of the velocity. On the right hand side there is a partial derivative of p with respect to x in the x component of the momentum equation. Then there is the Laplacian or the derivative of x component of the velocity with respect to all 3 coordinate variables, and then the x component of the body force. Again I'm saying equations को याद रखने की या रट्टा लगाने की किसी तरह कोई ज़रूरत नहीं है. X component of the Navier-Stokes equation अगर आप write down करेंगे तो it's simply rho because it's density du by dt, because it's the x component of the velocity, so we are dealing with the total derivative of the x component of the velocity here, minus partial p by partial x. Again, since it is the x component of the Navier-Stokes equation, so we derivate pressure with respect to x alone. Then mu, which represents the viscosity, plus into the Laplacian of del square u here, and in the y component you have del square v and del square w in these three equations. देखें ये जो तीनों टर्म्स राइट साइड पे अपीयर हो रही हैं, तीनों मुख्तलिफ तरह की फोर्सेस हैं. दिस इज ड्यू टू प्रेशर, दिस इज ड्यू टू विस्कोसिटी एंड दिस इज ड्यू टू द बॉडी फोर्स. सो ये तीनों किस्म की फोर्सेस हम यूज कर रहे हैं. नाउ द एनालिसिस ऑफ द Navier-Stokes equations. Well, the Navier-Stokes equations are to solve a variety of problems, such as for flow through wide parallel plates, flow through a pipe or a channel, etc. Note that these equations are non-linear equations in general due to the presence of the acceleration term, making the analytical solutions difficult to obtain, with the exception of simplified flow fields. ये equations non-linear equations हैं. अगर आपसे कहा जाए कि किस तरीके से non-linear equations हैं, कहाँ पे the non-linearity is occurring, so you should be able to point out the location or the terms which are making it non-linear equation. This pressure, the derivative of the pressures which are appearing here are, say, they can't be non-linear at this point and this stage. Then there is a double derivative of u with respect to x, and there is, you can't find any non-linear term here the way it looks like, but these are non-linear because of this. Yeah, they can be non-linear if this bx can be something different or can be something complicated, but they will remain non-linear whatever this bx and whatever this p may be, because of this total derivative d by dt, as d by dt is partial by partial t plus v dot del. इस कन्वेक्टिव पार्ट की वजह से ये Navier-Stokes इक्वेशन हमेशा नॉन लीनियर रहेंगी अनलेस अनटिल किसी कंसिडरेशन में, किसी फ्लो कंसिडरेशन में, किसी फ्लो डोमेन के अंदर दिस del dot v or v dot del or the convective rate of change becomes 0. On that case these equations can become linear, but due to this convective part occurring on the left hand side of the Navier-Stokes equations, these equations are non-linear equations and in fact non-linear coupled equations. Well, due to the presence of the acceleration term, these equations are non-linear equations, which makes the analytical solutions difficult to obtain. Well, there are exceptions in some simplified flow fields. कुछ simplified flow fields के लिए हम analytical solution of these Navier-Stokes equation find out कर सकते हैं, but mostly due to that convective part or that acceleration term, it is difficult to obtain the analytical solution of the Navier-Stokes equations. The three Navier-Stokes equations and the continuity equation for incompressible fluids contain 4 unknowns. कौन कौन से unknowns हैं? अगर इन तीनों Navier-Stokes equation x, y, z components of the Navier-Stokes equation और एक continuity equation को combine किया जाए तो ये 4 unknowns बनते हैं. इनमें से 3 the x, y and z component of the velocity, and the 4th unknown is the pressure itself. So ये 4 unknown है और 4 ही equations हैं, thus constituting a set of equations which would provide complete solutions if their integration for a given flow field were possible. देखिए फ्लूइड मैकेनिक्स की रिसर्च के अंदर भी इवन जब कोई गिवन फ्लो फील्ड का प्रॉब्लम आप सॉल्व करते हैं तो ये जो 4 इक्वेशन हमारे पास बनी है, ये आइडियल सेट बनाती हैं इक्वेशंस का, जिनको अगर हम सॉल्व कर सकें तो वी कैन डिटरमिन द फ्लो फील्ड कंप्लीटली. कौन सी चार इक्वेशंस? द एक्स कंपोनेंट ऑफ द Navier-Stokes इक्वेशन, द वाई कंपोनेंट ऑफ द Navier-Stokes इक्वेशन एंड द z कंपोनेंट ऑफ द Navier-Stokes इक्वेशन अलॉन्ग विद द कॉन्टिन्यूटी इक्वेशन. जब ये चार इक्वेशंस मिलती हैं तो इनमें चार अननोन्स हैं, एक्स वाई एंड z कंपोनेंट ऑफ द वेलोसिटी एंड द प्रेशर. तो ये चारों इक्वेशंस और ये चारों अननोन्स अगर हम इक्वेशंस को सॉल्व करके इन अननोन्स की वैल्यूज फाइंड आउट कर सकें तो वी कैन कंप्लीटली डिटरमिन द फ्लो फील्ड. बट केस टू केस वेरी करता है. सम सिंप्लीफाइड फ्लोज के फ्लो फील्ड्स के अंदर हम इनको बहुत आसानी से सॉल्व कर लेते हैं, एनालिटिकल क्लोज फॉर्म सोल्यूशन फाइंड आउट कर लेते हैं. समटाइम्स closed form solutions are not possible, so we go for the series solution, and when the flows are very complicated we move towards the numerical solutions of these equations. Yet the general solution of the Navier-Stokes equation, complete Navier-Stokes equation, remains unknown. These equations are still unsolved, so you can go for the solution of these equations, and best of luck for that. Well, other properties such as the density, the viscosity, etc. are assumed to be constant in the analysis in laminar incompressible flow configurations. Normal and tangential components of the velocity are zero at a stationary surface. These important properties are always true due to viscosity effects upon the boundary conditions for all laminar flow fields. Other boundary conditions will be described as they will arise during the solution of Navier-Stokes equation and the continuity equation for given flow fields. More complicated flow fields will require the computation packages and programs like Mathematica, MATLAB, Maple to solve these equations and determine the required flow field. Again, equations तो हमें पता चल गई, the x, y and z components of the momentum, the Navier-Stokes equation and the continuity equation, ये तो हमें पता चल गई जी. बाउंड्री कंडीशंस कैसे? बाउंड्री कंडीशंस भी प्रॉब्लम टू प्रॉब्लम वेरी करती हैं, एंड उन बाउंड्री कंडीशंस को देखते हुए एंड देन उस रिजल्टिंग इक्वेशन को देखते हुए हम अपने जो सेट ऑफ इक्वेशंस है उसको सॉल्व करते हैं, और जो वेल पोज्ड प्रॉब्लम है उसको सॉल्व करते हैं. जहाँ पे चीज़ें कुछ कॉम्प्लिकेट हो जाती हैं we use the Mathematica or Maple or MATLAB, these programming softwares and packages to solve these equations. And at this point for you people as well, क्योंकि मास्टर्स के स्टूडेंट हैं, you people are BS या MSc लेवल के ऊपर, you should be now learning these programs as well, because if you are willing to pursue your studies in mathematics and your research in mathematics, you are going to need these programs. So it's better to use these programs and make yourself familiar with them at present, so that you should be able to manipulate the basic equations in them whenever it is need to do so. जब भी न्यूमेरिकली चीज़ें कॉम्प्लिकेटेड हो जाती हैं तो हम उनको न्यूमेरिकली सॉल्व करते हैं, मेकिंग यूज़ ऑफ दिस प्रोग्राम्स. सो दीज आर वेरी हेल्पफुल प्रोग्राम्स. इवन कई सारी ये जो डायग्राम्स आप देखते हैं, मैं जो ये ड्राइंग वगैरह और ये सब कुछ जो फिगर्स ड्रॉ हुई होती हैं जो मैं ड्रॉ करता हूँ, दीज आर ऑल्सो मेड पॉसिबल इन मैथमेटिका. तो ये मेरी भी सारी ड्राइंग्स जो हैं और कैलकुलेशन जो हैं वो मैथमेटिका के अंदर ही होती हैं, पर्टिकुलर रिसर्च से रिलेटेड और बाकी चीज़ों से रिलेटेड. सो इट्स वेरी हेल्पफुल फॉर द स्टूडेंट्स एट दिस लेवल. इफ़ इट विल बी वेरी इंटरेस्टिंग फॉर यू एज वेल कि आप इनको देखेंगे कि किस तरह इन सॉफ्टवेयर्स को और इन पैकेजेस को यूज़ करते हैं आप फॉर द सोल्यूशन एंड फॉर द ग्राफिंग ऑफ द सॉल्यूशंस related to the problems of mathematics. These are very easy. You can learn them, and you can learn them by sitting at home. आप घर पे बैठे इनको सीख सकते हैं. These are very user-friendly programs, particularly the Mathematica. It's very user-friendly program, so you should go for it. It will be very interesting for you. जब आप करेंगे तो obviously only then you will find out that how interesting it is, and it will be very much helpful for your mathematics and for future research as well. Now the Navier-Stokes equations for ideal flow fields. इसके Navier-Stokes equation के certain cases हम discuss करेंगे and we'll see कि किस तरीके से Navier-Stokes equation को reduce किया जाता है मुख्तलिफ equations के अंदर. देखें ज़रूरी क्या चीज़ है और सबसे पहले क्या चीज़ है. I told you that Navier-Stokes equations are valid न्यूटोनियन या दूसरे अल्फाज में इसको कह लें कि रियल फ्लूइड्स और विस्कस फ्लूइड्स real fluids, Newtonian fluids, obviously there is and yeah Newtonian or the real or the viscous fluids moving with the velocity v. Now we have to write down the Navier-Stokes equations for ideal fluids. Now since for ideal fluids के लिए हम कैसे कर सकते हैं. What is the definition of the ideal fluid? If you try to recall that, it simply states that the viscosity is equal to 0 for ideal fluids, or there is no viscous effects present for this fluid. Substituting अगर म्यू इक्वल टू 0 सब्स्टिट्यूट करें आप जो Navier-Stokes equation के अंदर from 15 to 17, you will see that mu equal to 0 means this term will vanish, this term will vanish, and this term will vanish from the x, y, and z components of the momentum equation. In 15 to 17, we simply get rho du by dt is equal to minus partial p by partial x plus rho bx, or the body force x component, and the y component gives rho dv by dt is equal to minus partial p by partial y plus rho by, and rho dw by dt is equal to minus partial p by partial z plus rho bz. और अगर इन इक्वेशंस को, इन तीनों इक्वेशंस को बेसिकली हमने Navier-Stokes इक्वेशन के अंदर विस्कोसिटी 0 पुट की, या आइडियल फ्लूइड्स का केस जब हमने रिस्टोर किया और रीगेन किया तो हमें ये तीन इक्वेशंस मिली. और इन तीन इक्वेशंस को अगर आप थोड़ा सा गौर से देखें और थोड़ा सा एनालाइज करें तो यू विल कम टू नो दैट दीज आर द आयलर्स इक्वेशन ऑफ मोशन. ये आयलर्स इक्वेशन ऑफ मोशन है एंड दीज आर द रिड्यूस्ड फॉर्म ऑफ द Navier-Stokes equation. So we can reduce the Euler's equation of motion from the Navier-Stokes equation, provided that we substitute viscosity is equal to 0. अब viscosity equal to 0 पुट करने का क्या मतलब है? मतलब ये है कि हम Navier-Stokes equation कैलकुलेट कर रहे हैं या फाइंड आउट कर रहे हैं फॉर fluids with zero viscosity or for ideal fluids, and the force balance equation which governs the flow of ideal fluids are the Euler's equation of motion. So we get the Euler's equation of motion for this. So अगर Navier-Stokes equation के ऊपर आपकी grip और command अच्छी है तो you can simply say reduce the Navier-Stokes equation into Euler's equation of motion by substituting mu equal to 0. So these equations are हमने इसमें लंबी चौड़ी कैलकुलेशन या डेरिवेशन नहीं की, सिंपली हमने Navier-Stokes इक्वेशन के अंदर विस्कोसिटी को 0 पुट किया तो हमें Euler's इक्वेशन ऑफ मोशन मिल गई. हेंस कभी आपसे एग्ज़ाम में या किसी इंटरव्यू के दौरान या जब भी रिसर्च के अंदर आपसे कहीं से पूछ लिया जाए कि जनाब Navier-Stokes इक्वेशन और Euler's इक्वेशन के अंदर व्हाट इज़ द डिफरेंस, तो यू कैन सिंपली से that Navier-Stokes equation is valid for the Newtonian or the viscous fluids, whereas Euler's equation is valid for the ideal fluids, and we can reduce the Navier-Stokes equation into the Euler's equation by simply substituting viscosity equal to 0 or writing the Navier-Stokes equations for the ideal fluids. Now Navier-Stokes equations for fluids in static equilibrium. देखें जो fluids are in static equilibrium, for fluids in static equilibrium, जो fluids static equilibrium के अंदर हैं उनके लिए से change in velocity is equal to 0 or acceleration is equal to 0. So (15 to 17) equations 15 to 17 become 0 on the left hand side because dv by dt, or this was rho du by dt. Since velocity is constant or it's not changing, so change in the x component of the velocity is equal to 0. This is equal to 0 minus partial p by partial x. अच्छा, इस इक्वेशन 15 से 17 के अंदर अगर देखें तो अगर वेलोसिटी जो है वो चेंज नहीं हो रही, then the derivative of total derivative of the x component of the velocity, y component and z component of the velocity will vanish. And similarly, because u, v and w are not changing, so इनके तमाम derivatives with respect to the coordinate variables will also be 0. So this part will vanish and this part will also vanish. Simply we are left with plus rho bx rho dv by dt is equal to 0 is equal to minus partial p by partial y plus rho by and rho dw by dt, which becomes 0 and it is equal to minus partial p by partial y plus rho bz, which is the bx, by, bz are the x, y and z component of the body force. अब अगर इन इक्वेशंस को अगर आप थोड़ा सा गौर से देखें और थोड़ा सा रिकॉल करें तो these are the basic hydrostatic equations. So hydrostatic means, or the fluid in static equilibrium means that the change in velocity is 0, and when you substitute the consideration of static equilibrium or the condition of the static equilibrium into Navier-Stokes equation, you simply are left with the basic hydrostatic equations. So जब Navier-Stokes equation से the Euler's equation and the basic hydrostatic equations can be retained or can be retrieved when we substitute the value or the conditions of the two equations. Now, interesting thing is that कि किस तरीके से जनरली इन चीज़ों को रिड्यूस किया जा सकता है और जनरली Navier-Stokes equation को Euler's equation of motion and in the basic hydrostatic equation reduce किया जा सकता. Simply ये चीज़ ही बताती है कि Navier-Stokes equation is the generalized form of these two equations कि हम हाइड्रोस्टैटिक इक्विलिब्रियम की कंडीशन से और ज़ीरो विस्कोसिटी की कंडीशन से आज़ाद होके और इंडिपेंडेंट होके in a more generalized manner we write the Navier-Stokes equation. And the Navier-Stokes equation for the steady flow. For a steady flow, से ईटा से अगर रिप्रेजेंट करें पार्शल t is equal to 0 where eta is any fluid property. कोई भी फ्लूइड प्रॉपर्टी जो है वो टाइम के लिहाज से वेरी नहीं हो रही. इस एटा को डोंट मिक्स इट अप विद द एटा ऑफ द से वोर्टिसिटी वेक्टर. ये सिर्फ एक किसी भी रैंडम फ्लूइड की प्रॉपर्टी को रिप्रेजेंट करने के लिए एटा यहाँ लिखा है. इट कैन बी वेलोसिटी, इट कैन बी डेंसिटी, इट कैन बी प्रेशर. माई मीन टू से अगेन स्टेडी फ्लो के लिए आपको रिकॉल करा रहा हूँ कि स्टेडी फ्लो की प्रॉपर्टी ये है कि उसमें कोई भी फ्लूइड की प्रॉपर्टी जो है वो विद रिस्पेक्ट टू टाइम वेरी नहीं करती. दीज आर इंडिपेंडेंट विद रिस्पेक्ट टू टाइम. सो सिंस d by dt is equal to partial by partial t plus v dot del on the left hand side of equations 15 to 16, partial u by partial t is equal to partial v by partial t is equal to partial w by partial t are equal to 0, and only the convective part or rho v dot del v is equal to divergence of the Cauchy stress tensor plus rho b will survive. So the time derivative of velocity will be 0 for the case of steady flow. Now why these equations are called momentum equations? जिन लोगों ने, जिन बच्चों ने, जिन स्टूडेंट्स ने फिजिक्स पढ़ी है उनको मोमेंटम की डेफिनेशन तो ज़रूर पता होगी. Momentum or linear momentum is mass into velocity. जितना मास ज़्यादा होगा या जितनी वेलोसिटी ज़्यादा होगी मोमेंटम उतना ही ज़्यादा होगा. चेंज इन मोमेंटम total change in momentum is d by dt of mv, and or you can simply say that for constant mass, अगर मास कांस्टेंट है तो d by dt of mv is equal to m dv by dt. Also, as density is equal to mass per unit volume, so mass is equal to density per unit volume for unit volume and if we take the unit volume we are simply m is equal to rho in a quantitative manner. Dimensions will be obviously different for rho and v. Then d by dt of mv rho dv by dt. So these equations, और अगर dv by dt को आप देखें तो rho dv by dt is equal to d by m dv by dt is equal to m, or total change in velocity is the acceleration, so it is equal to ma. So the total change in the momentum will give us the force. So the force balance equation is basically the momentum equation, or the change in momentum. It tells about the change in momentum making use of these equations. So this is why these are also termed as momentum equation, but usually for the viscous fluid these are named as the Navier-Stokes equation. जब हम non-Newtonian fluids की तरफ move करते हैं तो then these equations are usually termed as the momentum equation obviously, and this is why these are called momentum equation. कि अगर हम momentum को derivate करें, उसका total change in momentum find out करें and totally derivate it with respect to time, we'll simply get the force, and this is why we call it the momentum equation. Now in today's lecture we studied about the Navier-Stokes equation, then we carried out the detailed analysis of the Navier-Stokes equation. We saw how to reduce it in the Euler's equation of motion and in the basic hydrostatic equation, and we learned that this is the most generalized form of the equation of motion compared to that of the Euler's equation of motion and the basic hydrostatic equation of motion. And with this I'll take you towards today's quote, and it reads that everybody is a genius, but if you will judge a fish by its ability to climb a tree, it will live its whole life believing it is stupid. हर किसी को बनाने वाले ने कोई ना कोई खासियत, कोई ना कोई खसूसियत से ज़रूर नवाज रखा. Unfortunately हम sometimes तमाम लोगों को एक ही किस्म की एबिलिटी से एनालाइज कर रहे होते हैं और क्लासीफाई कर रहे होते हैं, और यही वजह है कि उन लोगों को अपनी असल खूबसूरती या असल जो गिफ्ट है वो दिखाने का मौका नहीं मिलता. कभी भी डोंट लेट एनीबॉडी जज यू विद देयर स्टैंडर्ड्स. इंस्टेड अपने लिए खुद अपने स्टैंडर्ड्स सेलेक्ट करें, अपनी अंडरस्टैंडिंग डेवलप करें अपने बारे में, एंड ट्राई टू नो योर स्ट्रेंथ्स एंड वीकनेसेस. जब आप अपनी स्ट्रेंथ और वीकनेसेस से आगाह होंगे, सिर्फ उसी सूरत के अंदर आप अपनी स्ट्रेंथ्स को बेहतर तरीके से मैनिपुलेट कर सकेंगे और अपनी कमज़ोरियों को बेहतर तरीके से दूर कर सकेंगे. सो डोंट लेट एनीवन जज यू कि आप एक बहुत आउट क्लास आदमी हो जाएंगे अगर आप किसी दरख्त पे चढ़ जाएं या अगर आप ये काम कर लें. नो, सेट योर ओन स्टैंडर्ड्स. डोंट लेट एनीवन डिक्टेट यू द टर्म्स एंड कंडीशंस ऑफ योर लाइफ. नो, दिस इज नॉट द वे. यू हैव योर ओन मैनर, यू हैव योर ओन गुड. सो गो विद दैट एंड गो फॉर दैट. अल्लाह पाक आपको और आपके घर वालों को बहुत सी आसानियाँ दे. टिल आवर नेक्स्ट लेक्चर, इट्स अल्लाह हाफ़िज़ फ्रॉम माई साइड.